last lecture of this INSPYRE 8th edition. And I try to put together something mostly related with fundamental physics of what has been discussed this week, trying to kind of also put together a series of open questions. I'm not going to show you many new things with respect to what you already have heard before by yesterday. So, as you have seen, I put a title which is Q, from Quarks, quantum, kind of forced, black holes, and questions. And, well, as I was telling you already, this is a kind of an overview, of a summary, of a compendium of things we have learned this week, things which are open questions, and those you might contribute in the future, those of you who would like to study science. So, since this year we celebrate 100 years from the birth of this amazing person, Richard Feynman, I start with a sentence that he said, and I certainly agree with it. I would rather have questions that can't be answered than answers which can't be questioned. And I think that nowadays, seeing what also happens in the world, this is more and more true. Because there are so many people which don't question about world, about universe, about life. And this is not good. This is also to tell you that you should question even the thing which looks to be unquestionable. Keep asking questions. Even if somebody tells you, don't question that. Even if I would tell you, don't question that, you should question. This is the way to go forward, not only in science, where by definition it is, but I think usually in life. So I like this sentence. That's the reason for which I started with it. So let's see where we are. If we want to answer to this question, there are many ways to answer it. Certainly, one of the clear answers which has been coming together out of science is the fact that we are here, more or less. Meaning that in a galaxy which contains as many stars as neurons in our brain, more or less, we fortunately are a bit far from the center of our galaxy, because you might know that in the very center there is a 1,000,000 solar mass black hole, where in the periphery of this rather big galaxy, so the number of stars is not so small. And from here, it's rather amazing that just asking questions, we succeeded to understand not only part of the things which surround us, namely the visible part of our galaxy, but also the universe, at least up to the edge, up to 13 billion light years far from us, and to build up a story of the evolution and birth of our universe. So we are more or less here in the periphery of this galaxy, in a solar system which contains a certain number of planets. We also discover that perhaps solar systems are rather common in the universe, meaning not only stars, but stars which have around planets. And that's really a very recent information which is being enriched constantly. There are so many planets being discovered. We know already about 4,000, and more are coming. And this is, again, an amazing, amazing discovery. We have seen in the last days that the pillars of our understanding of the universe, it's 100 years old. It's, well, we call it modern physics. Maybe it would be proper to call it contemporary physics, because modern, it's going probably to change in whatsoever. And these pillars are two amazing theories, theory of relativity and quantum mechanics. I will say something about these two theories, not giving you mathematics or whatsoever else, but some concepts which I'd like to convey, especially related with quantum mechanics. So we all know that relativity, it's really fantastic theory which has been set, at least the ground, by Albert Einstein. And we see him here on the ray of light, just trying to travel with the ray of light. And this image tells us something more, a part of a simple kind of a joke. It's really at the origin of the theory of relativity, because Einstein, when he was a bit younger than you, he was at some point sick, as everybody is, and he received in gift, how it's called, a bussola, the compass. Thank you very much. So he received the compass, and he was really amazed of this miracle that it points always towards the same direction. And this kind of pushed him to think about what's the miracle behind this, about the electromagnetic field. And this kind of thought made him to wonder what would be if he would really, really be able to travel on a ray of light. And this seemed so weird to him. And there is also, in his some autobiographical writing, this kind of thoughts, and the beginning of the relativity saw him trying to imagine how the universe would look like if he would only be able to be traveling on a light ray. And since we were speaking about Einstein, you certainly, I think, you recognize him in this image, right? He was your age in this picture. So he was in Switzerland at this Aarau public school, and you certainly have recognized him. And I tell you that these guys are your age. 100 years ago, maybe actually more than 100 years ago, this is the way in which your age, kind of people look like. And they were asking questions themselves, as many of you already asked me in these days. So that's a very good sign. I think that the future has good hopes if I look at you. And, well, the relativity starts with a kind of a postulate. The postulate that there is a speed limit in the universe, which happened to be the speed of light, which is, in some standard, nowadays standard, if you look at our cars and our airplanes, it's certainly a big speed. If you start to look and start to imagine traveling through the universe, it's certainly a very small speed. So it's hard to say whether speed of light is big or small. Of course, depends with what you compare with. And the speed limit, it's absolutely consistent with the physics today if you change from the Galileo transformation to this relativistic, this is special relativity, which is not big deal in mathematics sense. It's of course big deal in rethinking space and time, and this of course has important implications, especially for those who work in accelerators, because you need to take this into account. And it was a question before, why you call this synchrotron light? Because synchrotron is the name of an accelerator which tries to synchronize the passage of particles with the relativity theory, which tells that if you don't take this into account, an accelerator will never work. So when you include relativistic effects into an accelerator and you synchronize the passage of particles in the magnet, taking into account time and space, you end up with synchrotron and with synchrotron light. So these are the new formulas which you might have or you will study. As I told you, no big mathematics, but conceptual. This is a big leap because you need to rethink space and time. And this has consequences. I'll show you, for example, the time. Time depends of who is the observer. So if I look at a clock and somebody who travels in a spaceship looks at the clock and I look at his clock, he looks at mine, some confusion might be appearing. And this confusion, at least embedded in special relativity, it's so nicely exemplified by the twin paradox. I'm not going to explain you the twin paradox, neither the solution, which is certainly there, of the twin paradox, but for those of you who have never heard about, it's a good way and a perfect time to have a look at the twin paradox, which it's rooted in the special relativity and finds a solution in the general relativity. So two twins which each one question who's older when they will meet again. That's an amazing paradox and a very good one to learn physics. The other pillar of our modern science, it's not only modern physics, that's I use science, because it's a pillar of biology, of solid-state physics, of nanotechnologies, of chemistry. Quantum mechanics, it's everywhere. It's valid, at least we know for sure that it's manifest strange behavior. It's especially valid for small object particles, atoms, molecules, where these features are not only providing nowadays technology, but also maybe the future ones, bridge towards future technologies. We have seen with Angelo Bassi, we have discussed a bit this peculiar feature of quantum mechanics, where particle and waves coexist in the same entity. So in quantum mechanics, we speak about particles because we have a source, for example, of electrons, even one electron at a time. But when we look of how electrons arrive, so how they shape their many-body behavior, so when we have many of them, what we could see is an interference pattern. And this has been quite puzzling in the past, continues somehow to be puzzling, if not for else, for the reason that this manifestation of the wave-like behavior, if you look at these many electrons, but on the particle behavior, if you look at the single dot, the single electron on the screen, going under the name particle-wave duality, it's itself hiding other aspects of quantum mechanics, like the superposition of states. So quantum mechanics, it's really an amazing theory. It's a pillar of the modern physics, and it uses these dual concepts, particles and waves, to explain the behavior we really see in the microscopic world. So waves and particles, which is valid not only for electrons. This would be weird enough, but maybe not so weird than the fact that this is valid for photons, namely electromagnetic radiation, and already I used two different concepts, but it's also valid for atoms, for protons, for molecules. It's even tested present day for virus. And it's still an open issue whether of course, in ideal conditions, if you are able to create these ideal conditions, you would see an interference with all conceptual difficulties you have seen with Angelo when we speak about the fast and the slow. So it's very difficult to see it. But if in ideal condition, you would be able to see interference of big objects, of really, really big macroscopic objects. And this has also brought to these paradoxes like this Schrödinger cat paradox, which is a manifestation, a macroscopic manifestation of this superposition of states. So a cat which is entangled, which means that it's having the same fate as a microscopic object, in this case a radioactive source, which has some probability to decay in some unit of time, let's say 50% probability. And the decay of this source, it's triggering a hammer which goes onto kind of a recipient containing poison. So if the radioactive source decays, cat is dead. If it doesn't, cat survives. That's a paradox invented by Schrödinger in 1936. So many, many years ago. Initially was passing unnoticed for many years, because the real essence of quantum mechanics and its interpretation, even if it was there, at least in Einstein, Schrödinger himself, was not fully appreciated, as well as not all the behavior of quantum mechanics were not fully appreciated from the very beginning. So this question about this superposition of states extending, namely entangled, in more correct word, with the cat, it's still an open issue. Is this possible? Is this not possible? So if we speak about big bodies, can we still have quantum features, at least conceptually? Or quantum mechanics, it's a theory which is going sooner or later to be replaced by another one of which the present quantum mechanics is only a limitation. So is there any theory beyond the present standard quantum mechanics? Angelo did not arrive to speak about this. He is one of the main proponents of this theory. So there is actually a proposal for a model which goes beyond the Schrödinger equation, which adds some additional terms which are, I don't want to puzzle you, but anyway, so are nonlinear terms. Nonlinear means that the collapse, it's naturally there, so you don't have a superposition of states any longer. And these additional terms are important for macroscopic objects. That's why you see them localized and not superposition of states. While for small objects like atoms and molecules, since there is a parameter there which depends on the size of the object, this object will keep being quantum for times much longer than the age of the universe. And why I show you this picture, what does it have to do with this, is the fact that I am leading an experiment, just trying to have hints of this new model. So we try to measure signals, if any, for the existence of these additional terms in the Schrödinger equation, which is called the collapse models, so collapse models. And what we try to measure in this amazing lab, underground laboratory, where there are many crazy experiments looking for dark matter, neutrino oscillation, we are also doing these experiments on quantum physics. And what we try to measure in this context, it's an radiation, so X-rays, which should not be there unless the collapse model is true. And for the moment, what we succeeded to do is to impose limits on the parameters of this collapse model. We didn't yet see any signal concretely belonging to the collapse model, but still we are rather 2 orders of magnitude far away to be able to close the case or to make it going towards a new road. So this is something very exciting because if we would really see this radiation, it would appear like a non-conservation of energy. That's why it's called spontaneous radiation. And then there is something there. Of course, the theory, you would expect that in the bigger theory, the energy is still conserved. Then you might wonder what happens with the counterpart of the energy you see as spontaneous. And there are some hints that the missing part is leaking into the dark energy sector. So it's a very edge research. It's the so-called high-risk, high-gain research. It's very, very exciting. So we are studying this kind of problem, but with also an eye to the future technologies. Because future technologies, quantum technologies, are deeply relying on quantum features. And if there is a threshold between quantum features from the micro world to the macro world, then we know that our quantum technologies need to take this into account in order to work. And the research goes on. There is present day many tests, not only tests of quantumness, but also technical tests, technology. So there are quantum technologies in space, and they are here and now. It's not something which is going to be here in 20 years by now. Maybe quantum computer is not yet here in the shape that we can use it more competitive than present-day computer. It was a question on this. It might come, but certainly, at least for cryptography, quantum technology, it's here, and it's being used, as I already told you. So with these two pillars, modern physics, it's certainly a very successful theory. So we have the speed limit and the size limit. So we see that for speed limit, when we go to small speed towards light speed, we go from classical mechanics to relativistic theory, to relativity theory. Again, if we combine the size, if we look at the size, we have for going from classical mechanics to quantum mechanics for very small objects. If we go into the extreme regime of high speeds and small sizes, meaning particle physics, we end up with the quantum field theory. And this is the standard model of particle physics. It's the quantum field theory relying on quantum mechanics and relativity theory. Okay, we have also seen this week some instruments for our understanding of the universe, for exploring this magnificent universe, from very small size objects, accelerators, to big ones, namely gravitational wave antenna, for example, or some telescopes. And unfortunately, we couldn't see, because it's working, the Daphne accelerator. It's 24 hours on 24. Only the small group who has done the working group here could see it, because they had the privileged day, the people working on Daphne, that it was a small problem, so they could enter inside this accelerator. So our instruments are accelerators, for example, smaller but very ambitious, like Daphne, which produce very peculiar processes, but also big accelerators. We have seen yesterday Large Hadron Collider and what it has produced and which are its ambitions for the near future, the dark matter frontier, or anyway, to look for some new physics. We have seen that part of these instruments are very complicated. And they ask a lot of effort. They put together thousands of people and many, many different countries. This is a kind of an image. You have seen this already yesterday. So all the embedded technology and knowledge, it's really at the threshold. So much a threshold that some of these technologies were not yet there when the accelerator or the machine started to be in the research and R&D phase. So they had to be invented or created while going along construction of these devices. And some of them found applications also in life and in societal application. We have seen some of them this week. So with the help of these instruments, at least for what concerns the microscopic world, what we could see is to check that the atom is really a universe. It's a universe which is complicated. And it collects together many interactions, electromagnetic for sure, if you look at how electron stays around the nuclei, around the nucleus. Strong nuclear forces between protons and neutrons and their structure, but also strong weak forces involving neutrinos if we speak about atoms or nuclei which do decay, do feel the weak decay. So we go on in this direction, and nowadays we are at this quark level. Now this, what we know here with the help, I use this slide by purpose, just to tell you that it's rather old. Now it's the advent of LHC. We can already exclude quark dimension until 10 to minus 18. So we didn't find a quark substructure for anything which is smaller than 10 to minus 18, which does not necessarily mean that quark does not contain other particles, simply that we do not know. We can definitely say that the structures, if any, within quark cannot be bigger than 10 to minus 18. But if somebody tells you, look, if you go to 10 to minus 21, you will find something, we can't exclude that. It might be. We need accelerators, different accelerators, and we have also seen yesterday different concepts of accelerator, which might, in the near future, bring us there and help us to go with this limit smaller and smaller, and maybe finding something new, looking something extremely new objects. So this is the Q, one of the Q quarks in our lecture. We know 6 of them. The names have nothing to do, of course, with their reality of particles which are also waves. And I think that those who have looked carefully at the movie, The Sense of Beauty, a part of the art science, but at some point there were some movies which showed this kind of microscopic world where fluctuations, vacuum fluctuations, field fluctuations every now and then popped up and produces what we call particles. So what we know today is that for the quarks, we know 6 of them. But only 2 of them, up and down, are components of our world, our stable world. You, me, the table, the sun, the moon, are made of these 2 quarks. Of course, one might then question, how do you know that others do exist? We know because they belong to particles which has been produced either in accelerators or before accelerators were even built, in cosmic rays interaction with our detectors. And this has been very fruitful in the 30s and 40s. Now we have accelerators which can, at least to certain energy range, be very effective. Beyond a certain energy range, we didn't have a talk on this because we couldn't talk on everything, but if you want, you can have a look by yourself at Auger experiment in Argentina, which is still looking for cosmic rays of extreme energy, far beyond what we can produce in accelerators. Good, so these are our quarks, and this is our standard model. You have seen it repeatedly this week, so I hope I don't bore you to show it to you again, but I show it to you again with a reason, to tell you that this model, it's the result of an adventure of a century of research. 100 years of research has come out with this output. It's elegant, it's beautiful, and it works very good. The Higgs boson discovered only 5-6 years ago, it's the completion of this success, But as again repeatedly has been told to you, we also know that this model, it contains its very beginning of problems. This model does not contain gravity. And this is somehow surprising. It's surprising, it's embarrassing, and it shows the thing that there is a lot of things still to do. Gravity, you remember, I showed you in this table, this model, it's quantum and relativistic. Gravity, the general theory of relativity, I'll come to it in shortly, does not contain the quantum theory. So it doesn't include the main ingredient of the universe. And this is really, really a problem. So we can describe the atoms, we can describe somehow the process in the sun, but only partially, because already if you look at a star is stable due to two opposite forces. The nuclear processes, which we have a description in the standard model, which would make the star explode, if not for else that gravity pulls things together. So this equilibrium between explosion induced required by nuclear forces and gravity, which would implode the star, keeps this object stable, but we don't have yet an understanding of the gravity in quantum context, which doesn't mean we have no understanding of gravity. We do. But the general relativity theory of Einstein, it's a classical theory. It doesn't speak in terms of particles. It speaks the language of forces, attraction. There is no intermediate. There is no graviton yet discovered. So it's not the same as the other forces description. It's a very successful theory. Sure, it is. It speaks about space and time. It gives this elegant formula, which is actually a condensate of many different equations. So these are differential equations in matrices. So these are tensors, which in fact are 4x4 matrices. So beyond that, this equation realizes an amazing unification. It's unification between space and time and matter. All what it is here, it's geometry of space and time. All what it is here, it's matter and energy. And it's really, really amazing that between them we have the symbol equal. This is really amazing. So geometry of space and time, it's generated by mass and energy distribution, while the movement of mass and energy, it's directly generated by geometry, by space and time. This has peculiar effects, like the one which probably you have seen with Viviana, in the sense that time and space are depending on gravity. And the dependence goes such that the time is passing slower in strong gravity field. So as strong the gravity is, the time passes slower and slower and slower. And you might have seen this movie. Who did? Okay. So this is Interstellar, and if you remember, in this movie, when they go on this planet to explore it, to look for possible conditions for life, at some point he says, let's speed up everything, because each hour we stay on this planet, there are 7 years for those left home. And this, in principle, it's physics. It's not fantasy. I've been seeing this movie with a friend who is not physicist, and she was telling me, oh, look, look what imagination this movie director had. I told her, no, this is physics. She remained completely shocked, because people usually do not know this. They even do not know that if I take my watch, and if I would have an atomic watch, if I keep it here, or I keep it here, the time is different. This is closer to the center of Earth, so time passes slower. So here it's slower than here. Of course, I don't have an atomic watch, so it's not important. But if you would have, and there are atomic clocks, which are able to measure time differences in few centimeters on Earth, and this is used also in metrology. We lately, namely 2 years ago almost, we had a confirmation, last missing piece of confirmation of the general relativity, because we have seen these gravitational waves. So they have been discovered by the 2 LIGO antenna, interferometric antenna you have seen yesterday, and Virgo in Italy, so United States. Now we have 3. And 3, it's much bigger than 2. Not as a number, but in power to do something. What to do? To localize the source of gravitational wave. With 2, you can't. With 3, you are at the edge of being able to do a triangulation and to localize the source of gravity, of this. You have seen, I don't want to insist on this, that the first gravitational wave that have been discovered belong to collisions of black holes with the mass around 30 masses of our sun. They come together, they induce oscillations of this object, of this gravitational antenna. Actually, somebody of you asked me how this is possible. So what happens is that the 2 arms are perpendicular, and they oscillate differently. Of course, that the wave has a kind of a direction, so this induces different oscillations of the 2 arms, and this induces of the radiation of the lasers which propagate a shift in the interference pattern. So that's how you see it. You see the shifts in interference pattern which signal to you the arrival of either an earthquake or of a gravitational wave. That's why it's important to have 2, 3 antennas far one of each other to avoid to mistake the gravitational wave of with an earthquake or with the train or with whatever makes noise. Oh my God, what is this? This is a point to tell you that, think about, this gravitational wave have been sent to us. So when this process happened, when these 2 black holes collided, happened more than 1 billion years ago. That's the time needed to the gravitational wave to travel to us. And this was far before the dinosaurs came on Earth. Dinosaurs were here 260 million years ago. So the dinosaurs were yet to come when really those black holes came together before the dinosaurs. We have seen this, Viviana showed you this, that now we have already statistics. We know that from gravitational waves we have at least 4 events, more are to come. And this, as yesterday Sergio Bertolucci was saying, it's a surprise. Nobody really expected this abundance of black holes with this mass. Is this something new? Certainly it is. How these black holes were produced? It's rather weird. And why they are so many? Many, 4 is not many. What it is many, it's the fact that if you extrapolate this to the universe, you come up with big numbers. So this might tell us something new about the universe and the distribution of origin of the black holes. They might come from processes which have been there right after the Big Bang and not necessary from the explosions for the end of life of big stars. We also know the universe not only, of course, from the gravitational waves, which is the last one which arrived, but from many other instruments. We have this image, beautiful image of our universe, which puts together all our knowledge, which is an image which it's very, somehow, it's very artistic and it's very touching. But we also know that this image is not all what it is there, unless our theory is wrong. Because while we were celebrating the fact that we have an image of the universe and we might have understood it, we have run into this puzzle of the fact that we are having missing pieces. Universe, it's not known. Actually, it's mostly unknown. And again, yesterday, it has been said that dark matter and dark energy seem to be here to stay with us. And they come from very accurate measurements. That's why precision is important. It's not only important to explore the edge, but it's important to make extreme precision measurement of what you think to know, because there might hide the novelty, which is what happened here. So the measurement of the speed of the stars in periphery of galaxy produced this inconsistency, which what we can calculate. So if you can calculate, knowing that the speed depends on the mass of the galaxy, if you go farther away, extreme periphery, if you have still stars there, they should move with a very small speed because they are far away, while we measure completely different. Star keeps having a high speed. And this, it's either a failure of our theory, and there are still some physicists who claim that, or the fact that there is additional mass, moreover, a halo extending far beyond what we see, which was called dark matter. So dark matter seemed to be here to stay. So much that even a galaxy has been recently found, which seemed to be made of 99.9% of dark matter, because there are very few stars there. So much that we might wonder, are there galaxies completely built of only dark matter? We might see them with gravitational lensing, but that's another story. Again, another view of the universe and additional information, especially regarding the expansion of the universe, has produced new data. So again, precision. Precision, it's a threshold. And it's important to make precision measurements. Precision measurement of far receding stars, supernova, so the supernova far away from us, has produced this result that the expansion of the universe, it's not constant, but it's accelerating. So the universe expands faster and faster. What can produce this? It's like a kind of an energy which pushes the universe to expand faster and faster. This is called the dark energy. And it's probably the biggest mystery of present-day physics. You have again seen this also yesterday. So we are all here, apparently, in this small fraction of the universe. The rest should be composed of dark matter and dark energy. We also have seen that there are some models, particular supersymmetry, which has the elegant solution that, based on symmetry concept, Whatever particle of matter has a counterpart of force, and whatever particle of force carrier has a counterpart of particle. This is supersymmetry. And this supersymmetric particle might be much heavier than the one we know, standard model. If so, but we don't know yet if this is so true, if this is true, we have candidates of dark matter. And these are being looked for already for years. It's still in the plan for the next years of Large Hadron Collider here, so smashing protons at high energy. We hope that some dark matter candidate might pop up. Complementary, again, in the underground labs, you have large detectors, xenon, for example, which are looking for interactions of dark matter coming from the space this time with our detectors, hoping to be able to see some of these interactions. For the moment, we didn't see it. So since it was quite some discussion here about the below 0 Kelvin, I wanted also to make this point in the dark energy discussion. So dark energy is much more difficult. We have much less hints of what it might be. So this is a problem, the problem that we don't know what dark energy is. And in the paper I gave to you, you might distribute it, at least the link among the WhatsApp group. There is some final comment related that this might show the way towards the dark energy. So I don't comment further, but I wanted to include it because some of you asked me about this. This, of course, it's depending, again, the quantities of dark matter and dark energy are going to be driving forces of how the universe will evolve. And that's something very exciting. Somebody has asked yesterday what will happen to our universe, and some answer has been given. In the present-day solution, the universe will be very, very, whomever might be very lonely there, because nothing around will be seen. But we don't know. Okay, but in the universe we also have black holes. Not only because we might have seen there, and this is the first direct signal, the gravitational waves, but we have indirect, namely the way in which the light goes around the black holes. So what happens if we would jump into a black hole? This is some question which I've been asked very often. First of all, I'd like to ask you, if it would be proposed to you, I put you on a spaceship and send you in a black hole, so you can check by yourself, are there candidates to go there? 1, 2, good, good, good. Okay, then let's put it differently. If I push you into a black hole, that you want it or not, but I give you a choice. Do you choose a big one, billion times the solar mass, or a small one, 30 times the solar mass? Who is choosing a small one? I push you there, a small one. Who wants to be pushed in the small? Who wants to be pushed into a big one? Choose the big one. Choose the big one because who jumps into a small one gets spaghettified. And that's not my invention. It really happens. Because the gravity at the edge of the black hole, namely at the event horizon, it's inverse proportional to its mass. Bigger the mass, smaller the gravity. If the gravity is very big, you will be pulled so strongly, and the difference between the pull on your legs and your head, it's so big that you will get spaghettified. So jump, if you are obliged to, in a huge black hole. One of the hugest is the one with 17 billion times the sun mass, which has, you see, a radius around 4 light days. It's really big. And in this one can really survive for millions of years. Nothing happens. You can't go out. But you can survive. At least nothing happens. That's the density. What happens if you jump into a black hole? We don't know. We can imagine that you might get interstellar travelers or even inter-universes travelers. We don't know. This is physics, though. It can happen. In order to get to know it, we believe we need to have the quantum gravity, namely understanding of space and time structure and its intimate structure. We imagine space and time as a continuum, but they might be built of atoms of space and atoms of time. we don't know. There are some proposals, like the string theory, which kind of unifies gravity with a high price of the extra dimension, where particle is a string which vibrates in this multidimensional 10 or 11 dimension space. Wonderful, great. This has also the appendix that it predicts existence of 10 to the 500 parallel universes, each one with its own physics. So physics, it's not the same in this. So we don't know whether this is a beautiful mathematical concept or has anything to do with reality. There are many years that this is here, but we will see what will happen in the future. So I approach the end of my presentation, and as a conclusion is to tell you that we know a lot. We really have discovered that the universe has been produced, staying to our present-day theory, in an event around 14 billion years ago. It was hot, amazingly hot, with quantum fluctuations, which has generated matter and seeds of structures of what we see today. We know that the matter today is not everything. There are dark matter, dark energies, or different physics. They are there as questions to us to be answered. And if we think a little bit, we also come from there. So you see, in this would be kind of the Big Bang, and we can trace our origin there. We were once light, and that event has produced life. This event has produced also us. The other thing is we know about the structure of the matter, but we also know that the structure of the matter, as we know it, can't really explain all this universe. And I end up again with Richard Feynman. And I think this related with other Q, which was in my title, questions. It's very appropriate. If you want to solve a problem that we have never solved before, we must leave the door to the unknown ajar. So please leave this door open, and let's try to go together, those who want to join us in this effort to contribute to a better understanding of this magnificent universe. This is our group picture, and just to tell you that I really hope to see some of you here back again, and why not, if not here, in other labs in the world or in other contexts, and contribute to understand better these mysteries, open questions, or else to applications for life, for society, of the magnificent things which are coming from our discoveries. If you want to stay in touch, at least with me, these are my contacts. You can contact me both on emails and on Facebook. I would be really happy to stay in touch with you and to learn what you will do in your future. And if you have other questions, like the thermodynamic group out there, just don't hesitate to ask. So I hope you enjoyed this course. It has been, of course, going too fast. I wish you a lot of good luck and success. Now it's not finished. We are now having a kind of a fiesta, final fiesta, because we give you, in a kind of a nice way, your certificates. So first, that's the end of my talk, but not the end of it, because we have to deliver to you your certificates. So thank you very much. Thank you very much. Now,